Please welcome to the stage for the laureate presentation, Dr. Kim Jones.
Thank you so much for that introduction, and thanks especially to Sir Leonard and Lady Emily Blavatnik for hosting this wonderful event. For those of you in the room that were not familiar with my research before this film, you might have imagined that this image represents how I carry out research in chemistry. But I'm not someone that stands at a lab bench mixing chemicals. And I'm also not someone who wanted to be a chemist from when I was a small child. I always liked maths and the sciences, and when I got the opportunity to use computers and even do little bits of things approaching computer coding, I enjoyed that too. But in the end, for my degree, I decided to focus on chemistry, because while I was interested in maths and computer science, I decided to focus on just chemistry to start with because I wanted to learn how to apply chemistry and make a practical difference. And as you're about to see, in the end, I have found a way of mixing together chemistry, computer science, and maths. My research is in the area of materials chemistry, and we all know that new materials can transform our lives. Consider the smartphones in our pockets. It is new battery materials that have allowed our electronic devices to get smaller, but still to have increased power. Currently, the time frame to find new materials is at least 15 to 20 years, and we need this process to be quicker, especially if the rate of discovery of new materials is slowing down despite increased effort. We're facing global challenges such as resource scarcity and climate change. New materials could provide us with an efficient way to generate renewable energy or to produce clean water efficiently. What I propose is that the number of possible materials is so vast that there is the ideal material out there for each of society's needs. So what's the problem? It's that even if we assume that there is the ideal material out there for each of these problems, how do we find them quickly, given our urgent need to do so? But why is it so difficult to discover new materials? One of the problems is scale. The search space is enormous. If you think of materials built from organic molecular building blocks, which is my line of research, then estimates would suggest that there could be up to 10 to the 60 possible molecules. This number, 10 to the 60, is larger than there are atoms in the solar system. And only a small fraction, about 10 to the 8 of them, have ever been made by mankind. And so how do you find the needles in the haystack that are the materials with the necessary properties to help us? Well, the second problem is one of complexity. You can't design a material in the way that you can design a building by drawing a blueprint. These Lego people know how to build their home, because when you look at a Lego brick, you immediately know how that brick can and will connect to other bricks. And Lego can give you a set of steps that would result reliably every time in a Lego house. Unfortunately, atoms are not Lego bricks. Atoms are not as easy to assemble, for example, in the manner shown at the bottom of the screen. Instead, they assemble in ways that are not always easy to predict, and there are so many factors in terms of their composition, arrangement, and form that can't be trivially controlled. Yet all of these factors also influence their properties, and this means it's very difficult to do inverse design, which is to come up with a list of properties you want in a material, and then design the material that fulfills those needs. So how do we discover new materials currently? We can think of it as if we're trying to explore the vast map of possible materials, each known material represented here by a circle, where only a few have been explored and their properties are thus known to us. I would argue that most big step changes in new materials have been discovered largely by chance until now, but there are vast regions of this space that we've still not explored at all. So all the black space on this slide, and in fact actually beyond this slide, represents materials that we don't know anything about. If we now zoom in on one of these possible materials within this vast landscape, perhaps this circle represents graphene, and it has amazing properties. We then make small changes to modify the graphene in an effort to get a material with even better properties. Now, each of these connected circles represents a slightly different form of graphene that might have slightly different properties. We've also got good at doing computations to search that local space, and we can now evaluate tens of thousands of possibilities within that region to identify other materials that someone should make based on the promise of those materials' predicted properties, rather than slowly exploring possibilities based more on guesswork. But if we zoom back out again, even if computation is helping us with high-throughput screening, then we've still got this vast map of possible materials that we don't know about. For example, what if there's a material up in the top right corner? How do we even begin to search for such a material, let alone evaluate its utility? And that's a big part of what my group does. We're looking for materials for a range of applications, including capturing solar energy and materials for energy storage. But we have a special focus on porous materials, which can be used, amongst other ways, in molecular separations. I will explain what a molecular separation is in a moment, but for now I wanted to highlight what may be a rather surprising figure to you. It's estimated that molecular separations account for around 10 to 15% of the world's energy consumption, and many of these separations are done by inefficient processes that we could improve by discovering a new material for the task. So what are molecular separations? Well, you want to be able to separate out mixtures of many different molecules so that you have each molecule individually. Chemists and engineers perform separations to purify feedstocks for things like polymers and pharmaceuticals. Without these crucial separation steps, there could also potentially be harmful impurities in the products of chemical manufacturing. Molecular separations are hard. You are often trying to separate out two things that differ only very slightly. They may have the same chemical composition, but differ only slightly in shape. So one way you can think of molecular separations with molecules that differ only by shape is as a children's toy, in which the child must insert blocks of a certain shape through the corresponding hole. In this image here, we want to separate out the two differently shaped molecules, represented by a blue cube and a yellow cylinder. However, you need exquisite control of the pore size and the shape of the pores of the material. If the holes are too big, or in our case, shaped so that both molecules can go through, then you end up right back where you started with a mixture. However, if you were able to change the hole dimension slightly, some of the blocks pass through, while others are successfully separated out. And now you end up with separate piles of blocks, or in our case, molecules. So as I said, molecular separations account for 10 to 15% of the world's energy usage, and currently about half of the molecular separations that we do are carried out using distillation processes. The process of distillation is one that involves boiling mixtures or freezing them, which is incredibly energy intensive. But if you can replace any of these distillations by a membrane-based separation, in other words, doing the separation more akin to the process of the children's shape sorting toy, then you use about 90% less energy. For every different separation, though, you will need to design a new membrane material that is suited to that specific separation task. So how can we use computers to design these materials? Ideally, you would want to develop a membrane that would be optimal for a specific separation, while also being cheap enough to make on a large scale and to meet other requirements, such as being stable over a long period. This image is of some of the classes of porous materials that we research within my group. Essentially, we're trying to tailor these materials such that the void space is the right size and shape to separate out molecules that are diffused through the material. But there exists an enormous number of possible porous materials. And at the moment, new membranes are mostly discovered by small changes to known systems and best guesses based on chemical experience of those synthesizing them. And this is incredibly inefficient. So what we do is to explore this enormous range of possibilities on a computer. And importantly, we aim to explore systems that wouldn't be found by chemical intuition alone. One part of our work has been to develop open source software that can automate the assembly and testing of materials. Here is an example of a short piece of computer code that would automate building and testing the porous molecules shown on the right. Due to the enormous number of possible materials, even on a computer, we cannot test them all. So we have included an evolutionary algorithm within our software to help us find new materials efficiently. Just like the finches of the Galapagos Islands slowly evolved differently shaped beaks that could be used for specific functions, Our software can similarly be used to identify molecular building blocks that could be used to develop new porous materials. If you start with a generation of 100 systems built from a library of building blocks, the software then introduces random changes in some of the molecules or swaps some of the features of the molecules and then obtains the next generation of molecules, much like survival of the fittest in nature. By doing this over many generations, the molecules get better suited to the task, and we can create better materials than before. This is an example from my research where we asked the algorithm to produce molecules with larger internal cavities. As you can see, we were successful in generating a series of successively larger molecules through the use of this evolutionary algorithm. But one problem that we've been particularly focused on is that we are able to make predictions of wonderful new materials that have promising properties, but it's meaningless if our synthetic collaborators can't actually make these materials in the laboratory. So when we go to our collaborators, excited about our predicted material with amazing properties, their reaction is not always, great, let's go make this in the lab. Rather, they envisage all of the challenges that they might encounter in synthesizing such a material, one of which might be that it will not be safe to make. To solve this problem and to make sure our experimental collaborators are able to make the materials we predict easily and quickly, we've been working to integrate machine learning and artificial intelligence into the process. We have asked our experimental collaborators to rate lots of molecules as to whether they would be able to synthesize a particular target in 5 steps or fewer at a reasonable scale. And then we've trained a machine learning model to better predict what sort of structures we can incorporate into our porous materials while maximizing the chance that our predictions can be realized in the laboratory. And so here we have an example of a porous molecular material that would be relatively easy to make on the left-hand side via using our machine learning model, compared to a much more difficult molecule on the right-hand side that was predicted beforehand. And with that, I wanted to emphasize that it is vitally important that we train our young chemists of the future to be highly computer literate, with skills across data and computer science too. Chemistry is moving in a new direction, and we have powerful tools at our disposal that we, and especially our next generation, can exploit to discover new molecules and materials more rapidly. Before I finished, on another note, I wanted to mention how difficult the pandemic has been for scientists as it has been for wider society. Here I am during spring 2020 with my then 2-year-old daughter, who thought she was helping me do some research during lockdown. We must all make sure that we pay attention and do what we can to mitigate what will be the long-term effects of the pandemic on science. The effects have not fallen equally on scientists and future scientists, whether due to caring commitments, lost lab or school time, or many other difficulties and missed opportunities. So let's make sure that we don't lose the future scientists that's going to find the next revolutionary material. And very importantly, I'd like to thank firstly my collaborators and also my group members, both past and present. Here, some of them are shown in a Zoom event during the pandemic as egg self-portraits. And finally, I'd like to thank my family and friends, and particularly my husband, Martijn, and daughter, Rosalind, shown here. Thank you.